Hey guys, it is final exam eve, so today we're going to be going through several problems, the first of which is going to be the maximum flow problem from class. So, in the last lecture, he did promise that there would be a problem on the final exam that was similar to, or almost identical, he said, to the one that he gave in class. So what I've done is I've read up on it, and I have made up this example of a max flow problem that I think might look something like what you might see on the exam. And, well, I've designed it to cover pretty much every case that you might run into. So we're going to use it to describe maximum flow, we're going to use it to describe the min-cut theorem, we're going to use it to show how the back edges work, we're going to use it for everything. And it should get the idea across for you. And then you can take this exact same example, go away with it, and tinker with it. Try doing it different ways. Get different, try to get a different flow. You won't. Okay? That's the idea. So, first, what's the goal of the algorithm? Well, the point is to send as much of whatever commodity we're talking about from S to T along these positive weighted edges. So, the only rule that we really have to be considerate of is the conservation of flow. So, whatever we send into a vertex, whatever amount we send into a vertex, must then immediately leave that vertex. We can't store anything. So, even though I can legally, for example, send 10 from S to A, I cannot send that same amount from A to D. I can only send 5, so I'd have to leave 5 behind here, which is not how the problem works. So I'd have to send 5, and then 5, and then 5 to get to T. I can't send 10. There's no sending 10 and then breaking it off. Can't do it like that. And we'll show how that's denoted visually. We'll show how the construction of the residual graph works, and I'll show you how I think the most efficient way to enumerate that visually is. Okay? So let's, then we'll talk about the complexity. We'll do a separate example for the complexity, because I think complexity is best understood through example with the maximum flow problem. It's not like most graph problems. This is actually the complexity is directly related to how the problem works, very clearly and intuitively, unlike in most cases. So let's get started. Let's take that original path that I said before. We'll do S to A to D to T. So we're bottlenecked here by 5. You can see that's the minimum value along the path, so we have to send that amount. Well, or we could send less, but why would we do that? So, we're going to send 5, which means that we have a capacity of 5 remaining on this outgoing edge because we sent 5. Okay? So these back edges essentially allow us to traverse backward, putting capacity back into the edge. So it would just work the same way. We would subtract whatever we send from here and add it back over here. And now we have 0 left here because we sent 5. And now we have 5 left here because we sent 5. And we'll just continuously, as we do these iterations, we'll update our flow count. And we will be done once we no longer have a clear path to get to T. Once we can no longer traverse whatever edges we need to get to T. If we start hitting zeros and we can't get there, maybe it's as simple as all of these are zeroed out. I usually try to zero these guys out first, just because I think that's more fun. But you can do it however you like. That's the whole point. Try doing it however way you like and see if you get the same flow that I did. Okay, so what else can we do? We can't use this anymore. So we can kill this guy off, I think. Yeah, we can kill this off. So we can send 5 here, 5 here, 5 here, and then 5 through here. So we're going to go S to A to B to E to T. So now we've used up all 10, and we have, we've used up all 10, we have 0 left, and because we've sent 10, we have 5 left here, because we sent 5, and we have 0 left here because we sent 5, and we have 5 left here because we sent 5. That's a 5. I assume there's going to be more. Oh, yeah, there's more. Alright. Alright, so we'll do S to C to E to T, because we can clearly, this is dead now, we can't use this. That's why I like doing it that way, because it's quicker. I don't have to check the graph for 0 edges. I can just look right here and see, alright, we've only got 1 edge left that we can even use to get anywhere from S. It seems simpler to me. But you'll do it however you like. So we're going to send 5, because we're bottlenecked by 5 here, and then we have a capacity of 5 left. So that's actually going to kill this one off. And yeah, let's see what happens. 5, because we sent 5. We have 0 left because we sent 5. And we've sent a total of 10 here. So now we have 0 left. We have 5. Let's see. No, we're actually done. We can't get anywhere, you see, so we can send 5 from here, but this is this edge is leading into C, so we can't leave, we can't use this 15. We have a 0 here, so we can't go that way. And this is dead, so the maximum flow is 15. And if you want to verify that, there is and this will probably show up on the exam, the maximum flow min-cut theorem, which states that the capacity of so the minimum capacity cut, its capacity will be equal to the maximum flow. And so what do I mean by minimum capacity cut? Well, you take a cut of the graph such that you have 2 separate sections of the graph, S and T, where S and maybe some other nodes are in S, and T and maybe some other nodes are in T. The capacity of the cut is the summation of the weights of the edges leaving S and going to T. And you're looking for a cut like that such that it's minimized, such that that capacity is the smallest. And that will be equal to the maximum flow. So that's another way of finding it. Or in my case, it's a way of verifying that I'm right. So I made this a simple enough graph that we can easily do that. So we see that if we cut here, we have these 2 edges, so we have a capacity of 20, 10 and 10. If we cut down here, we have 5, 10, and 15. If we try cutting, say, maybe we cut along here, if we cut along here, then we would have 10, 15 as well. If we cut here, we get 10, 15, 20. If we cut here, we get 20. So you see the minimum cut is 15. And those 2 numbers will always be equal. That's an observation in graph theory. So how long does it take to run the algorithm? The algorithm itself runs in O of E times the maximum flow. Why is that? Well, let's look at an example. Let's say we have a graph, do a simple one. We have, say, A, B, C. Yeah, that'll do. We'll have our sync node over here. We'll give these capacity 1000. Okay? And we'll just give these capacity 1. So eyeballing it, if you were doing this by hand, obviously you would just send 1000 here, cancel this whole thing out, send 1000 here, cancel this whole thing out, and instantly in 2 moves, you as a human would get flow equals 2000. Alright? And that would be fine. But a computer might not do that. A computer relies on depth first search or breadth first search, and we don't know exactly what it's going to do every time. So, in the worst case, what might happen? Say your depth first search goes from S to A to B to C to T, because that's a valid path, right? We have positive weighted edges going along the whole way. at that point, you have 999 left here. 0 left here because you sent 1, and 0 left here because you sent 1, and then 999 left here because you sent 1. Okay? Next, it can't go down here because we have zeros going down, but worst case scenario comes down here, S to C to B to A to T, because now we have these positive weighted edges going up the graph. So you get 999. 0, because you sent 1. 0, because you sent 1. 999. So your flow is being summed up like this. And then, continuing on the worst case scenario, we'll do one more iteration of this. You send one more this way. Okay, so now we're at 998. And we have 0 left here. We're going down these positive 1 edges because we sent 1. And now we have 0 left here again, going down because we sent 1. 998 plus 1. And you can see the pattern now. So we're just going to keep going like this over and over again 1,000 times. So every edge in the graph will be traversed 1,000 times. So just keep summing up one by one in the worst case. So that's maximum flow. Hopefully it makes sense. Anybody has any questions or wants maybe more examples? I mean, there's not a lot of time, but go ahead and ask me. I think if you just putz around with that one graph, keep trying to do it in different ways. There are lots of ways to do it. I've done it several ways just on that graph before filming this. And there are lots of ways to do it. You always get 15. And your min cut will always be 15 because the graph is not changing. So yeah, up next we're going to try to do some NP completeness reductions and maybe some master theorem stuff. I don't know. I mean, if anybody's watching this, just shout out what you'd like to see if I haven't already done it, and maybe I'll get to that. I'll be doing this all day. Thanks.